Welcome to part 1 of our lesson on first-order ordinary differential equations. Today, we will explore how rates of change, initial conditions, and time stepping allow us to model physical systems computationally. By the end of this session, you should be able to explain what a first-order ODE represents and implement a basic Euler stepping method. We will also compare our numerical results with known analytical solutions and learn to use a professional solver from the SciPy library. Why do ODEs matter so much in physics? Often, the laws of nature do not give us the final position or temperature directly. Instead, they give us rules for how things change over time, such as radioactive decay or Newton's law of cooling. Mathematically, a first-order ODE relates the derivative of a variable to a function of the variable and time. Because a derivative only describes the rate of change, we always need an initial condition to determine exactly which solution curve we are on. We will start by importing the necessary Python libraries. We need NumPy for numerical arrays, matplotlib for visualizing our solution curves, and the odient function from SciPy for numerical solving. The output simply verifies that our packages have loaded successfully and that NumPy is ready to go. Before using professional solvers, it helps to understand the explicit Euler method. By approximating the derivative as a finite change over a small time step, we can update our values step by step. Here, we begin defining a Python function to perform this manual time stepping. This part of the code sets up the core logic for the Euler method. We create an empty array to store our solution, set the initial value, and begin a loop that will march the system forward in time by multiplying the current rate of change by the time step. The code concludes our custom solver function by returning the completed array of values. This simple loop captures the fundamental idea behind all numerical ODE solvers. With the function successfully defined, our custom Euler stepper is now ready to use on a physical problem. Our first worked example is exponential decay, which models processes like radioactive decay. The rate of change is proportional to the amount remaining. We also have the exact analytical solution involving an exponential function, which we will use as a benchmark. Here, we translate our physical parameters and initial conditions into code. We define the decay rate function, establish a time array, and calculate both the numerical Euler approximation and the exact analytical values. This block of code handles the visualization. We plot the analytical solution as a continuous line and overlay our Euler numerical solution as points, so we can visually inspect how well they match. The resulting plot shows the classic exponential decay curve. You can see that our orange Euler points follow the general trend of the blue analytical line, but they slightly diverge from the exact solution as time advances. The printed output confirms this discrepancy numerically. The final value computed by the Euler method is a bit lower than the true analytical value at the end of our physical time interval. This error occurs because the Euler method assumes the rate of change remains constant across the entire time step, which is not true for exponential decay. To see how the time step size affects accuracy, we set up a loop to test 4 different step sizes. Inside the loop, we call our Euler stepper for each of the different step sizes. We calculate the maximum absolute error for each run and plot all the resulting numerical curves together for comparison. Finally, we display the plot and print out the maximum error we recorded for each of the tested time step sizes. Looking at the plot, the impact of the time step is clear. The orange dots representing the largest step size drift noticeably away from the true curve, while the purple dots with the smallest step size track the exact solution much more closely. The printed text quantifies what we just saw visually. As we decrease the time step from 1 second down to 0.1 seconds, the maximum error drops significantly, proving that smaller steps yield better accuracy. At this point, we should draw a clear line between physical parameters and numerical settings. The decay constant dictates the actual physics of the system, while the time step size is purely a numerical knob we turn to control our computational accuracy. While the Euler method is great for learning, Real scientific computing relies on robust, tested algorithms. We will now introduce ODINT from SciPy, a professional solver that automatically handles time stepping to maintain high accuracy. To use ODINT, we must define our derivative function using the specific argument order the solver expects, which is the dependent variable first, then time. We then pass this function, the initial condition, and the time array into the solver. This snippet prepares the plot to compare our new ODINT result against the exact analytical solution. It also calculates the maximum difference between the two to evaluate the solver's precision. Notice the shape of the output array. For a single ODE, ODINT returns a two-dimensional array with one column. The first 5 rows show our quantity smoothly decaying from the initial value of 100. The plot confirms that the ODINT solution is practically indistinguishable from the analytical curve. The two lines overlap perfectly, demonstrating the power and reliability of a professional solver. The output shows that the maximum difference between the ODINT result and the exact solution is on the order of 10 to the -6. This confirms that the solver is highly accurate. Because ODINT returns a two-dimensional array, we sliced out the first column to plot it against a one-dimensional time array. Next, we will write a compact block of code to compare the analytical, Euler, and ODINT approaches side by side. This portion of the code completes the visual comparison. We plot all 3 methods together using different markers, and then print the maximum errors to summarize their computational performance. In this comparison plot, the green squares from ODINT lie exactly on the analytical line, while the orange circles from our manual Euler method drift slightly off the true path. The error output provides the final verdict. The Euler method has a noticeable error of about 3.4, whereas the ODINT solver reduces the error to a microscopic level for the exact same physical model. Now it is time for some guided practice. I encourage you to pause the lesson and modify the decay constant to see how the physical system responds. Then, alter the Euler time step to see how the numerical approximation reacts. For your final practice task, review the ODINT code provided in this starter cell. Try to identify exactly which variables represent the physical parameters, the initial condition, and the numerical time array. This block simply plots the results of the practice cell. You can tweak the initial parameters in the previous slide and rerun this code to see how your changes affect the visualization. Here is the baseline plot for the practice code, showing the correct exponential decay for an initial amount of 80. As you experiment with the parameters, watch how the steepness and accuracy of this curve change. To summarize, an ODE provides the rate law, the initial condition gives us a starting point, and computational solvers turn those rules into a solution curve. In Part 2, we will apply these concepts to more complex physics models.